Hi everybody, and welcome to this talk on dynamic membership management. Thank you to the few brave souls in here who are willing to stay all the way to the end, this being the last session. Thanks to UBRI and Apex, of course, for hosting these things, and specifically UBRI for supporting our research at Reykjavik University. It allows us to do these things that we love to do. And my name is Hafsteinn Hjartarson. I'm a PhD student at Reykjavik University, where I am studying permissioned blockchains, focused on chains in that are and blockchain systems that are specifically designed for enterprise use. So I am focused on the usability and management of these permissioned systems, and the current title of my thesis is Architecture of Enterprise Systems in the Era of Blockchain. And I use the word current title because being in this industry, it's very hard to stay in your lane because things are changing and happening so fast all over the place. You get very tempted to switch topics. I'm about 1.5 years into this degree, and this is the second title I have for the thesis. I don't remember what the first one was. As I said, I'm focused on enterprise systems and the architecture of building these systems, both from the ground up, like the software side of these things. I come from a software engineering background and been a developer for many years. But also the interoperability and the connectivity between enterprise-level blockchain systems and legacy centralized systems. I'm focused on the reliability of these systems because, as we know, if we are going to be living in the enterprise world, these companies, they need permissioned chains, they need permissioned systems, which allows them to have control over who gets to do what in terms of functionality and data, and so on. It's very important to be able to control access and such things. And we are focused on decoupling mechanisms from services. So whatever we do, we are writing a series of papers now where we isolate essential building blocks of permission chains and talk specifically about them and try to come up with stuff that permission blockchain only essentially needs to work and nothing else. Everything else gets moved up to the service layer. So in our paper, we published a paper on dynamic membership management. It's not been published yet. It's been accepted to the Springer's Cluster Computing Journal. It's pending publication, actually. And in that paper, we talk about something we call annál. So annál is an old Icelandic word. It means an order of past events, ordered in a timely fashion within 1 year. So this is often a TV show at the end of, on a New Year's Eve in Iceland, called News Annál. We talk a little bit about this thing in the dynamic membership management paper, so I decided to touch on it just a little bit here. It's actually an experimentation blockchain. It's a very simple blockchain. It does nothing except build a ledger. And we use it to test things quickly because we know how it works. It's very simple. There's no validation built into it, no incentives, no nothing. It's essentially just a distributed time-stamping service. There's a coordinator for each round. It coordinates the current round and then hands the coordinating responsibility over to the next node. And at most, one block is produced each round. Like I said, it's completely separated from the service layer. It does nothing, no validation, no incentives. It's very policy-driven, so we can configure it. It's highly configurable, which is very good when we are testing new things. It's lightweight with very low overhead. It has an OFN message complexity in the normal case operation, as I will show you. And the blocks are very simple. We have the coordinator ID for each block, who coordinated the round when this block was produced. We have the winner ID, who created and wrote the block. We have a body or a payload field You don't have to write anything in there, or you can write whatever you want. No validation or verification. We have the hash of that current block, and of course the hash of the previous block for the immutability feature, and we have the signature of the winner, of the one who created the block. So just to go through the protocol very quickly, we have 3 RPCs, like I said, but this is a simplified image. So right before the request numbers message gets sent, the coordinator starts by initiating the round by sending a prepare message to all the nodes. And for the bootstrapping round in anode, we use the node with the lowest ID, which starts as the first coordinator, and the next coordinators are then selected selected in the round-robin fashion. So before the request numbers stage, there is a prepare message sent from the coordinator to n-1 nodes in the network, where the coordinator is asking each node to create a random number, where we use a Python pseudo-random number generator, create a random number, hash it, and send me the hash of the number. And every honest node who is participating will do this, and it will send the hash to the coordinator. The coordinator will store all these hashes, and having those, it will send a prelude message again to n-1 nodes, asking for the actual random number that the node used to create this, the hash. So the nodes will do that, and then we are located there in the request numbers, where the coordinator is in the top line there, and then we have 4 nodes, 0, 1, 2, and 3. When the coordinator has received all the random numbers, it will create like a generalized sum by XORing all the numbers together. And finally, to select the winner, it will use this general sum and calculate the distance from the sum to each random number. And the random number with the shortest distance will become the winner of the round. So the winner is then announced to the network. The winner creates their block and disseminates it to the network. And because every writer, and when I talk about nodes, I'm talking about writers. I'm just looking at this from this experimentation blockchain when every node on the chain is a writer or a potential writer. Because they become coordinators at some times, and regularly over time they become coordinators every once in a while. They all know how to calculate the sum, and they all know how to verify the winner, so they do verification on those things. So they redo the sum. Every node in the network redoes the sum, calculates the distance, verifies that their hash and their random number was correctly received by the coordinator. And if everything is fine, they send a confirm message to the coordinator saying that they agree, this is the winner. And then they also send a confirm to the next coordinator saying that, all right, so now you can start the next round. We have a few versions of this where we are creating these random numbers, or we are creating random bit strings of various lengths. And we are also experimenting with starting the next round before the first round finishes. So basically when the winner has been selected, you can immediately start the next round. But the next round's block addition does not complete until the round before has been declared a success. So we are now at the time where I'm going to be talking about what I said I was going to talk about, which is dynamic membership management framework. Now this is a conceptual framework that we wrote a paper on. It's conceptual in the terms of we do not see this as a specific case. This is more like a general way of thinking about how we can do dynamic membership management, because we see that in a lot of current chains with the big players out there, these methods of managing the active writers that are actively participating in the consensus, very important players. These methods are very ad hoc, so Ripple's doing it one way, Ethereum has another way, and so on. And we just wanted to try to generalize what we know, or to just congest the information that's out there, see what's happening, and kind of just give some guidelines on how to think about these things. So the dynamic membership management framework that we have come up with has a few important components. The heart of this thing is called the membership authority. Now the membership authority, or MA, it has a two-way connection to every node, so that it can query nodes, and the nodes can query the MA, and it can initiate communication, it can send data to other nodes. And in the paper we talk about this MA thing as a centralized entity, identifiable by a single URL, but it can really be set up in any way. It can be a centralized RESTful API service. It can be just another node on the network, or a smart contract somewhere, or even a DAO or whatever. It doesn't really matter. It just has to have this two-way connection and the correct protocols on each side. So what the MA does is it's responsible for keeping track of all the members in the network, how they are progressing through each round, how they are, like their performance metrics are, and to do this, it keeps a membership version going. So during bootstrapping, we have membership version 1. And the only thing that triggers a membership version update is when a node either enters or exits the network. Besides this, the MA is also responsible for adding new nodes or accepting new nodes into the system or the network. And it's also responsible for kicking out bad behaving nodes and removing nodes that have requested to be removed. It's like Annaut. It's heavily. It runs on policy, so it's highly configurable. Every aspect of it, and it keeps metadata on every node participating in the network, and even a list of previously. Of nodes that have previously been a part of the network. So just to talk very quickly about the process of entry and exit, this is a part of the MA. This is based on policies first and foremost, but this is like what you see on the image there is what every MA does. This is like the base of what the functionality of adding a node is, but the steps in there are configurable. So to accept a new node, a node sends a request to enter to the MA. The MA adds the node to a waiting list, and it starts a validation process. And this is what I'm talking about by policies. You can decide how does the MA do validation on entering nodes. This could be things like, does the node have the correct certificate? Is it coming from a certified domain, or what have you? This is configurable. If the node does not pass validation, it just gets removed and even blacklisted. But if it passes validation, it gets added to a candidate queue, where the node waits until it gets added to the actual network. And the only reason it has to wait is if there's potentially not a space for a new node yet. This is something that the MA keeps score of. The MA has rules on how many writers are allowed to participate in the network at any given time. So to add this node, all that the MA does when the node is in the candidate queue, all the MA has to do is circulate a new version of the membership management, which says that all right, everyone needs to update their version and include this new node, and here's the information on it. So when everyone has received this information, they will start connecting to the new node, and the MA will remove it from the candidate queue. So To exit, for a node to exit, it sends, it's just pretty much the same way. It sends a message which is a request to exit the network. The MA will circulate a new membership version with this new node removed, and when the node that wants to exit receives the new version, it can be sure that, okay, the MA has sent it to everyone, I can just log out. Nodes can also be removed by force or kicked out for bad behavior, or if they're malicious or broken or just not responding to anything. And it's exactly the same thing. It's just a new circulation of a new membership version. Additionally, we have, and finally, we have this concept of a penalty box. This is just like a timeout or a naughty list. If you don't behave well in the network, you get added to the naughty list. So good nodes, they participate in the consensus in an honest manner. They keep score of other nodes, like how reliable do I think other nodes are in terms of like what is the time that takes them to reply? What is the rate of their, like how often do they reply or not reply? How often is their output, their result or their view of the output of the consensus round the same as the majority? And these things, they occasionally could become coordinators, and they contribute to the system as a whole. And that's like how we view, like I talked about that there are no incentives, but we view that participation in a good, robust network is an incentive by itself. Bad nodes, on the other hand, they will be sent to the penalty box for bad behavior. They will stay in the penalty box for an exponentially growing number of rounds. They started by staying there for 4 rounds, and each time they are sent there, it just gets longer. Finally, the current coordinator that is coordinating a round, it may decide to, instead of immediately starting a new block addition round, it may decide to do like a little bit of a garbage collection where it views the status or performance status of every node and throws the least or the one with the lowest score to the penalty box. So this is happens at a scale because we are at a very the time scale of this is very small in comparison with block additions or rounds. Because we are viewing this in the scope of enterprise systems, we can allow ourselves to optimize for very reliable servers with very high uptime, because they are just fully managed and managed by these companies. So we have run a lot of simulations on this. And this is just because I was talking about the penalty box. You can see the number of failed nodes there is denoted by F at top of the tables there. This is very similar to how Ripple does it with the UNL. They have this unique node list which tells the nodes, okay, you should connect to this portion of the list and you should connect to another portion of it. But they also have this concept of the negative UNL, where every 256th ledger, which is called the flag ledger, a node might get sent to this negative UNL. So it's a very similar concept, but at a slightly different time scale. So these are the simulations that we did. Ran each simulations. We ran this multiple times. Each simulation is run for 1 million rounds. You can see on the left there, we have several different sized networks. The N is then ranges from 20 to 200. And for each round, we have a certain number of nodes that are allowed to be in a failed state, denoted by F there. We also configured the nodes that at any given time, a node has a 95% chance of being in a valid state and a 5% chance of being in a faulty state. And there's no relation between rounds, so at every round they always have the same odds of being in a faulty or active state. Finally, we have, you see tau there set to 600, which denotes that if a node goes into or transitions into a faulty state, it will stay faulty for the next 600 rounds. So the table above is without the penalty box, and you can see that having very few, having F at a very low setting, it just says that, okay, for this round to be successful, F is 0, no node is allowed to be in a faulty state. If there's even one in a faulty state, the round will not finish successfully. So there's a low chance of that happening when you have many nodes, like 200, 0% chance, or 0% of the cases. At the bottom there, you can see that we have introduced the penalty box, and then the rate of successful rounds increases a lot. And you can see the dark gray cells. This is where the performance or the reliability of the system as a whole surpasses the reliability of each individual node. So when it gets above 95%, we highlight it, and that's where we want it to be. Yeah, so this is pretty much it. If you are interested in taking a look at this paper, you can just send me a line on LinkedIn or come talk to me. Pursuing a PhD degree is often very lonely, so I would love to talk to someone about these things. You can also message me on LinkedIn. It's right there if you want. I can send you the paper. And yeah, just thank you very much.